August 2007. Goldman Sachs, one of the most sophisticated quantitative trading operations on Earth, watched their flagship Quant fund bleed 30% in a single week. Their risk models, built on decades of financial theory, PhDs, and hundreds of millions of dollars of compute, said this was a once-in-a-100,000-year event. It wasn't. And the reason it wasn't, the reason nearly every financial crisis in modern history was impossible according to the models, comes down to one single assumption. One equation. One bell curve. The normal distribution. Welcome to Quantifea. I'm your host, a financial engineer with degrees from World Quant University, and today we're going to destroy the most dangerous assumption in all of quantitative finance. And then we're going to build something better. Let's get into it. Before we burn it down, we need to understand why the normal distribution became finance's default assumption in the first place. The normal distribution, also called the Gaussian distribution, is described by this probability density function. F of x equals 1 over the square root of 2 pi sigma squared times e to the negative x minus mu squared over 2 sigma squared. Two parameters. That's it. Mu, the mean. Sigma, the standard deviation. It's mathematically beautiful, symmetric around the mean, and it has this incredible empirical property called the central limit theorem. The average of independent random variables converges to it, regardless of the underlying distribution. That's why it appears everywhere in nature. So in the 1950s and 60s, when Harry Markowitz was building modern portfolio theory and Fisher Black and Myron Scholes were pricing options, they did what any good scientist does. They reached for the most tractable distributional assumption available. They assumed returns are normally distributed. Under this assumption, a 1 sigma daily move happens 32% of the time. A 2 sigma move? About 4.5% of the time. A 3 sigma move? Less than 0.3%. And a 5 sigma event? The probability is about 2.87 times 10 to the negative 7. If you assume 252 trading days per year, that's one 5 sigma event every 14,000 years. Except the 1987 Black Monday crash was a 22 sigma event. Long-term capital management's 1998 blow-up involved returns beyond 6 sigma. And Goldman's Quant quake in 2007? 25 sigma on multiple consecutive days. The model doesn't just get it slightly wrong. It gets it catastrophically wrong in precisely the scenarios where getting it right matters most. Market crashes, liquidity crises, contagion events. So why does finance keep using it? Partly inertia, partly tractability, and partly because in calm markets, with short windows and diversified portfolios, it's a reasonable approximation. The problem is the tails. And that's what we need to talk about. To understand fat tails mathematically, we need to talk about moments. Not moments in time, statistical moments. These are summary statistics that describe the shape of a distribution. The first moment is the mean, where our returns centered on average. The second moment is variance. How dispersed are returns around that mean? The third standardized moment is skewness, whether the distribution is symmetric or if one tail is longer than the other. And the fourth standardized moment is kurtosis, and this is today's protagonist. Kurtosis is defined as the expected value of x minus mu to the fourth power, divided by sigma to the fourth. More precisely, we work with excess kurtosis, sometimes called Fisher's kurtosis, which subtracts 3. Why subtract 3? Because when you compute kurtosis for the normal distribution exactly, you get 3. So excess kurtosis measures how much heavier your tails are compared to normal. Excess kurtosis of 0, normal. Greater than 0, your distribution is leptokurtic, meaning it has fatter tails and a higher, sharper peak than normal. Now look at real data. The S&P 500 daily returns have excess kurtosis somewhere between 4 and 7, depending on the sample period. Bitcoin, often above 12. Student T distributions with few degrees of freedom can have infinite kurtosis. Infinite, meaning no finite fourth moment exists. And here's the critical consequence. When you zoom into the tails of a leptokurtic distribution versus the normal, you see the gap. That gap, that seemingly tiny strip of extra probability mass out in the extreme tails, is where 5 sigma events live. Is where 25 sigma events live. Is where every financial crisis in modern history lives. The normal distribution assigns these regions a probability indistinguishable from zero. Real financial returns do not. This is not a minor calibration error. This is a model that is fundamentally, architecturally wrong about the most important part of the distribution. Theory is one thing. Let's look at what the data actually shows. Here's a stylized histogram of daily S&P 500 returns, the kind of empirical distribution you get when you pull decades of price data. The x-axis is daily return, the y-axis is frequency. I've overlaid the normal distribution fitted to the same mean and standard deviation. See the problem immediately? The bars in the middle are roughly in line with the curve. That's fine. But look at the tails. The empirical bars extend well beyond where the normal distribution says there should be almost no probability. The bars in the tails are taller than the curve, sometimes dramatically so. At 4 sigma, the normal distribution predicts a probability density of roughly 1.34 times 10 to the negative 4. Real equity return data at that level is typically 10 times more frequent. And at 5, 6, 7 sigma, the gap becomes astronomically large. There's a standard diagnostic tool for this, the quantile plot, or QQ plot. If your data were perfectly normal, every point would fall on this straight diagonal line. What we actually see with financial return data is an S shape, and crucially, the tails curl above the line. That curl is the signature of fat tails. The empirical distribution puts more probability mass in the extremes than normal predicts. And now we can locate every major market crisis on this distribution. Black Monday 1987, 22 sigma under normal assumptions. LTCM in 1998, beyond 6 sigma. The global financial crisis of 2008 produced multiple single-day moves beyond 7 sigma. The COVID crash of March 16, 2020, 8 sigma. Goldman's Quant quake, 25 sigma on multiple consecutive days. Under a normal distribution, each of these events has a probability so small it should never occur in the entire age of the universe, let alone in a single century of stock market history. And yet here they are, every decade. Like clockwork, the data is telling us something the models refuse to hear. So now we know the normal distribution fails, and we've seen the empirical evidence. But why do fat tails exist? What generates them mechanically in financial markets? There are 3 key mechanisms, and understanding them matters for building better models. First, volatility clustering. This is the GARCH effect, named for the generalized autoregressive conditional heteroskedasticity model developed by Tim Ballerslev in 1986. In real markets, volatility is not constant. Large moves tend to cluster together. A turbulent day is followed by more turbulent days. A calm period begets calm. In GARCH 1, today's variance depends on yesterday's squared shock and yesterday's variance, a feedback loop. Even if individual shocks are conditionally normal, the unconditional distribution, what you observe over time, has fat tails. This mechanism alone is powerful enough to generate much of the excess kurtosis we observe in equity returns. Second, jumps. The standard Black-Scholes model assumes prices follow a continuous diffusion, geometric Brownian motion. But real prices jump. A company misses earnings and gaps down 15% overnight. A central bank surprises the market. A geopolitical shock hits. Robert Merton's 1976 jump diffusion model augments standard Brownian motion with a compound Poisson jump process. The jump intensity lambda controls how often jumps arrive. These discontinuities are impossible to hedge continuously, and they inject extreme outcomes into the tail of the return distribution. Third, and perhaps most insidious, correlation breakdown. In normal markets, assets in a diversified portfolio have modest correlations. The diversification benefit is real. But in crises, correlations spike dramatically, often approaching 1 across all asset classes simultaneously. This is the cruel joke of financial risk. The moment a tail event occurs is the exact moment your diversification vanishes. Assets you thought were independent move together, amplifying losses across your portfolio far beyond what any normal-based model predicted. These 3 mechanisms, volatility clustering, jumps, and correlation breakdown, combine to generate the fat-tailed, negatively skewed, heteroskedastic reality of financial returns. The normal distribution assumes none of them. Now let's translate this mathematical failure into something tangible. Value at risk, the dominant risk metric used by banks, hedge funds, and regulators worldwide. VaR at confidence level alpha is formally defined as the negative of the infimum of x such that the CDF of x exceeds 1 minus alpha. In plain English, the VaR at 95% confidence is the number such that on 95% of trading days, your loss will be smaller. It's a quantile of the loss distribution. Under a normal distribution, computing VaR is trivial. The 95% one-day VaR is simply mu minus 1.645 sigma. The 99% VaR is mu minus 2.326 sigma. These z-scores come straight from the normal quantile table. Simple, fast, analytically clean, and catastrophically wrong. Compare normal VaR to the VaR from a student T distribution with 4 degrees of freedom, a distribution with fat tails but the same mean and standard deviation. At 99% confidence, the fat tail VaR is roughly 1.8 times larger. That gap, that red bracket, represents losses the normal model simply cannot see, cannot price, cannot reserve capital for. In practice, this means a trading desk using normal VaR might believe it needs $100 million in capital to cover its tail risk. The actual fat-tailed distribution of its positions requires $180 million. That $80 million gap is not a rounding error. It's the gap between solvency and failure in a crisis. This is why we have conditional value at risk, also called expected shortfall. CVR is the expected loss conditional on being in the tail, the average loss when things go very wrong, not just the threshold. It integrates the shape of the tail rather than just reading off a single quantile. And it's worth noting, regulators figured this out. The Basel III Fundamental Review of the Trading Book, adopted in 2016, mandated a shift from VaR to expected shortfall as the primary capital measure precisely, because VaR undercaptures tail risk. The question is whether your model's caught up. All right, we've established the problem rigorously. Now let's talk solutions. What do actual quants and risk models use? The first and most accessible upgrade is the student T distribution. Originally developed for small sample statistical testing, it has found a permanent home in quantitative finance because of one key property. Its tails decay as a power law rather than exponentially. The probability density function involves the gamma function and a single extra parameter, nu, the degrees of freedom. As nu increases, the distribution converges to normal. At nu equals 5, the excess kurtosis is 6. At nu equals 4, excess kurtosis is theoretically infinite. At nu of 3 or below, the variance itself becomes undefined. When practitioners fit the student T to equity return data using maximum likelihood estimation, they typically find nu between 3 and 6. Goldman Sachs's models in 2007 reportedly used around 6 degrees of freedom, still underestimating the true tail thickness, as 2007 demonstrated. The second class of models takes Benoit Mandelbrot's insight from 1963 that financial data follows Lévy-stable distributions, not normal. The characteristic function of a Lévy-stable distribution has 4 parameters. Alpha, the tail index, controls how heavy the tails are. When alpha equals 2, you recover the normal. When alpha equals 1, you get the Cauchy distribution, which has no finite mean and no finite variance at all. The key visual insight is on a log-log plot. The normal tail curves downward rapidly, exponential decay. A power law tail, the signature of Lévy-stable distributions, appears as a straight line. That straight line represents dramatically more probability mass at extreme values. Mandelbrot's empirical estimate for cotton prices was an alpha of about 1.7, comfortably in fat tail territory. The third approach, and the current industry standard, combines GRCH volatility dynamics with fat-tailed innovations. The standard GRCH with student T errors captures both the clustering mechanism, why volatility persists, and the tail thickness within each period. Extend to GGR-GRCH and you also capture the leverage effect, the asymmetry where negative shocks hit volatility harder than positive ones. No single model captures everything. If you want to be closest to the full complexity of real markets, fat tails, asymmetry, volatility clustering, and occasional jumps, you need a model that combines all 4 features. So what do we take away from all of this? 3 practical commandments for every quant, risk manager, and serious investor. First, test your distributional assumption. Never assume normality for risk calculations without empirically verifying it. The Jark-Barrett test, which jointly tests whether the skewness and excess kurtosis of your data are consistent with normal, is fast and easy to implement. Under the null hypothesis of normality, the JB statistic follows a chi-squared distribution with 2 degrees of freedom. If your p-value is small, your data isn't normal. That's not a minor issue. That's a mandate to use a different distribution. Second, switch to expected shortfall. The formula for ES at confidence level alpha is the integral of VAR from alpha to 1, divided by 1 minus alpha. It's the average loss across the entire tail beyond your VAR threshold. Unlike VAR, it's sensitive to how bad the bad days actually are, not just how many of them there are. It's also subadditive. It respects portfolio diversification in a way that VAR does not. Basel III mandated expected shortfall for a reason. Third, model your volatility. A GARCH 1-1 with student T innovations has 4 parameters: omega, alpha, beta, and nu. That's just 4 parameters. And it consistently, dramatically outperforms normal IID assumptions in out-of-sample backtesting studies across every major equity market. The cost of ignoring volatility clustering is large. The cost of fitting a 4-parameter model is negligible. Practically speaking, every time you build a return model, run through this checklist. Compute your excess kurtosis. Test for normality. Model volatility with GARCH or at minimum report CVR alongside VAR. Do not calibrate exclusively on recent data. Recency bias creates tail blindness. And always stress test beyond 3 sigma. Keynes said markets can remain irrational longer than you can remain solvent. I'll add a corollary for quants. Models can remain wrong longer than you can remain employed. Build for the tail. That's a wrap on episode 1 of Quantifea. We covered a lot of ground today. We started with the normal distribution, its PDF, its assumptions, why finance adopted it. We built the mathematics of moments and kurtosis from the ground up. We looked at the empirical evidence in real return data, the QQ plots, the histograms, the historical crises that should be impossible but keep happening. We explored the 3 mechanisms, GARCH clustering, jumps, and correlation breakdown, that generate fat tails in practice. We dissected the VAR failure and built the CVAR solution. And we surveyed the better distributional models, student T, Lévy-stable, and GARCHT. If you want to go deeper, the single best book on this topic is Benoit Mandelbrot and Richard Hudson's The Misbehavior of Markets. Mandelbrot spent 50 years proving that financial returns follow power laws, not bells. It's readable, rigorous, and genuinely important. Link is in the description. Next week, we're building Ito's lemma from the ground up, the mathematical engine behind Black-Scholes, interest rate models, and virtually every derivative pricing formula in existence. We'll show exactly why classical calculus breaks in continuous time and what stochastic calculus does instead. Subscribe so you don't miss it. Drop a comment below. What's the most extreme sigma event you've personally lived through in the markets? I want to hear from you. This is Quantifea. See you next week.